Well, welcome again. Daniel Mast, Radiochemistry department. We're going to talk about some high pressure conditions here today. Only this time we're gonna do it a little bit differently. So today you've heard a couple of presentations about people talking about pressure, stress, strain, but we're going to take that beyond the limits of what you would normally encounter every day walking around with pressure on your feet, heels, and such. Beyond what you would find if you were at the bottom of the ocean, where you experience 100,000 times the pressure that you would at atmosphere, further into the Earth until you would get to the millions of atmospheres of pressure. So to do this, we use a device called a diamond anvil cell, as featured here. And these are just regular diamonds that many would find on rings or other pieces of jewelry. They really allow us to do extremely interesting and incredible things, because we can not only go to beyond the limits of normal conventional pressure devices, but we can also see inside them. So we can use a microscope and see crystals growing, different morphologies, as well as applying lasers, X-ray, and neutron techniques to see how is the structure changing. So for a simple case, like plutonium metal, with a little bit of pressure and temperature, we can see that there's 1, 2, 3, 4, 5, 6, 7 different arrangements that the atoms can take on. Now, if you know anything about plutonium, simple is really not a good word to describe it. But if we were going to go to a multi-atom system, such as I'm studying with molybdenum oxides, we can see more interesting behavior. As we pointed out before, there's this zigzag chain of octahedra here at ambient condition, and until a couple of months ago, this was the only structure, the only way that we understood molybdenum dioxide to arrange the atoms in this material. By applying modest pressures in the 25 to 70 GPa range, we were able to realign these into this orthorhombic symmetry system. And that's great. As I've said, squeeze things, they get smaller, they get more ordered, more efficiently packed, and you're conserving space. But we've seen in structures such as this that, the volume doesn't always just decrease. Sometimes it increases when you would expect the opposite. And this is because of those atomic rearrangements, the phase transitions. So using genetic algorithms and various DFT simulations, we've predicted that this simple 6-coordinated octahedra will shift to an 8-coordination. Now this is not the immediate instinctual expectation for what happens when you apply pressure to a simple material like molybdenum dioxide. But we're going to go look for this anyway because, well, we can. We can go to these pressures. We can go to these temperatures. We're allowed to push the limits on our understanding of materials properties and really our understanding of the world around us. So next week I'll be in Chicago performing this experiment with some of the members here in the audience, and hopefully we'll find something interesting to share with you next time. Thank you.